Hello, welcome back to another physics investigation via the core practicals. What we'd like to do this time is talk to you about a P1 practical. So this is in the Physics 1 paper and it's called Investigating Voltage Current Graphs, or looking at the characteristics of three very important electrical items. You've come across them many times before. I'm going to draw the circuit symbols for them now so you can remember, but one of the ones we're going to look at is the voltage current graphs for a fixed resistor. Then we're going to do it for a filament light bulb, and then finally for this rather unusual symbol, which is what we call a diode. And with diode, as is per the diagram here, you can see there's kind of a unique shape to it. There's an arrow going in one direction, and if you come from the other direction there's a dead end T-junction. And that's because diodes restrict the flow of the currents in one way or the other. What we're going to do, we're going to show you the circuit diagram here. So the circuit's all set up, and as is always the case when I'm investigating electrical circuits, there's only ever three things to talk about. There's the voltage, the current, and the resistance itself. And the three resistors we've got here, as we mentioned already, a fixed resistor, the filament light bulb, and the diode. So what we're going to do, we have to remember always that there's one equation that goes with this, and it's absolutely something you must remember for the exam, and that is V equals IR, where V is the potential difference, current is the flow of electrons that around the circuit, and the resistance is what gets in the way. All electrical circuits have some kind of resistance. If you like, it's a bit like electrical friction, so it will slow things down. Now what we're asked to do, or what you're asked to be able to remember for the exam, is what the voltage current graphs look like for these electrical systems. So we always set up the circuits the same way. You've done them many times before. I'm going to draw one just here to remind you. We need a power supply. On this occasion I've got the power supply unit, but it could be batteries. So I'm connecting them into my circuit, and then I'm going to put my device that's used to measure current, which is my ammeter, which I've got marked over here. That always has to go in the flow of the circuit. Then I've got my object, which I'm starting with my resistor, and if I complete the circuit, that won't work unless the circuit's complete, so the current can flow around here. But if I want to measure the potential difference across my resistor, I need to put my voltmeter there. Remember, the voltmeter has to go either side because it's trying to measure the potential difference. Now, that's my simple circuit. That's what I've got set up over here. I've put the light bulb in here so you can just see when it's on and when it's off. But I'm going to change that now. I'm going to take the light bulb out of my circuit. I'm going to put the fixed resistor in. This fixed resistor here says 3.9 ohms, and I'm going to pop that in there, connect the circuit back up again. You can see I've still got current and voltage readings, and what I'm able to do, I'm able to change the voltage on my device here. Now look, if you're back at the circuit here, it's quite straightforward to work out what happens. If you think of the voltage as the push or the energy that gets the electrons moving around the circuit, remember we're trying to talk about electrons flowing around the circuit, very small particles, and it's called electricity because it's the electrons that move. They don't move on their own, they need a push to get them going, and it's the voltage or the potential difference that gets them moving. If you remember that, then it's quite easy to understand what's going on, because the harder you push the electrons, simply the faster they will move. So the bigger the potential difference, the bigger the flow of the electrons. And we can see that right here now. So if I start, at the moment I've got a very low voltage, 0.3 volts. If I turn around and increase that voltage, 0.4, you'll notice the current's gone to 0.1. If I go up again, 0.6, the current's gone up to 0.14, and so on and so forth. And I can keep going like this, and if I plot a graph, it looks just like this. It produces a beautiful straight line, and unsurprisingly, it goes straight through the origin. Well, of course it does, because if you don't push the electrons, then they don't flow at all. And we call this an ohmic conductor. It's called a fixed resistor. It makes a perfect straight line. It's a proportional graph. You may have to plot that in the exam. Here's one we did earlier on graph paper, and this is what you would have to do if they asked you during the exam. On a higher tier paper, you may also be able to recognise that if I turn the voltage supply around, everything would work just the same. But this time, when you look at the current, if the voltage is negative, the current is negative. So it's exactly the same graph but going the other way, which will keep mathematicians happy because this is what we call a proportional graph. Okay, so that's for a fixed resistor. Now that is how we do the circuit. It's how you set the circuit up, how you measure the results. Shouldn't be a problem at all. However, they also want you to know what happens for a filament light bulb. Now you might think if I take this out and I put the filament light bulb in that it should behave exactly the same way, and it does, but the problem is this is not a fixed resistor. As the wire starts to heat up, as it does, the more voltage I put in there, the brighter my light bulb gets. If the light bulb is getting brighter, then what happens is the wire itself is getting hotter. And when the particles vibrate more quickly, it creates more resistance. If there is more resistance in the way, the electrons can't flow like they should do. So what we end up with is, I'll grab myself a piece of paper quickly. If I try to do the same again this time, and I plot my graph of voltage against current, it should be the case that the harder I push them, the faster they flow. And that works fine until the light bulb gets hot. When the light bulb gets hot, instead of the results increasing like they should do, the extra resistance stops the electrons from flowing, and as a result, the graph starts to level off. So for a filament light bulb, what happens is, in this region here, where the wire is getting hot, the resistance increases and the current can't, which is why it levels off. And if you look at the graphs that you'll see in the exam, again, it doesn't matter whether you go in the positive direction or the negative direction, you get a curve on the graph. Now there's one left to go, and the last one is what happens when we turn around and put a diode in the circuit. And as I mentioned before, the diode has an arrow on it to show electricity travelling just one direction only. If I try to plot the graph for that, what you end up with is still the same theory, that as you push the electrons with more voltage, the current increases. But if you try this time to push the electrons in the opposite direction, the semiconducting device doesn't allow the current to flow. So effectively a diode prevents you from damaging many electrical equipment by making sure the current can only flow in one direction. Easy to remember if you look at the diagram, an arrow to show which way the current can flow and a dead end to show that it can't. And when you look at the voltage current graph, it's a pattern which is quite recognisable. Hope that helps. Thank you very much.